All right. So this is the last lesson. Next class is a review day. Following class is a test. On the review day, we grade a quiz, we go over, prepare for your next quiz, you take that next quiz, we grade it, and you get to see how you did. But that's it. We don't spend a lot of time reviewing. It'll be up to you to start reviewing after we have done all of that. Okay? To finish things off, we're going to talk about asymptotes. Okay? It's more stuff with limits. If I look at this picture, I see I have a function that is trending towards this vertical line. We call this a vertical asymptote. There's no function value at the line, and I can see my function is either going down towards negative infinity, very, very large negative numbers, or up towards positive infinity. So if I gave this a coordinate like 2, we'd say x equals 2 is a vertical asymptote. I'm going to use VA for short, okay? Now, we're going to be looking at the behavior of our function around a vertical asymptote. Last class, we found whether or not we had a vertical asymptote and the locations of it, okay? So we found the location. Today, we are going to figure out, is my function going up or down to the left? Is it going up or down to the right of this vertical asymptote, okay? So we'll get to that. But before we get to that, we're going to talk about horizontal asymptotes. Now, we're not going to just focus on where do we have horizontal asymptotes. Instead, we're mostly looking at end behavior. I would say that as I approached larger and larger values to the left, so if I trended towards negative infinity, my function would be trending towards this y equals -1 line. So I would say y equals -1 is a horizontal asymptote. I'm going to use HA for short. And it's not really about if you have a horizontal asymptote or not. The questions will more be, what is the behavior of your function to the left or to the right? And what is the behavior function to the left and to the right of a vertical asymptote? So end behavior and behavior around a vertical asymptote is really what this lesson is talking about. Okay, now, using new terminology, this limit terminology, this is what we will see happens with a vertical asymptote. We will find that if we look at a value, we'll get a number over 0. Now, for this exercise, we will pretty much give you the number. You will not have to identify it. So that's given to you. But they will ask you, hey, what is going on just to the left of C of the function? And you need to figure out, are we trending towards positive or negative infinity? And the same is going to be asked of you of what's going on to the right of your vertical asymptote. And you need to figure out, are you trending towards positive or negative infinity? Okay? And that will determine, hey, at my vertical asymptote, to the left, am I going up to positive infinity values or down to negative infinity values? What am I doing? Am I going like this? Is it going to connect? Is it, not connect, but approach the same value? Is it going to both go down? This is what we're trying to figure out, okay? We'll get there. Before we get there, we will talk about horizontal asymptotes or end behavior. And what we will do is we will evaluate limits as x is approaching very, very large values, or as x is approaching very, very large negative values. I don't want to say small values because small values are thinking 0. 0.001. I'm talking about large positive and large negative values. Look all the way to the right and all the way to the left. The question is, what is my function doing? Is it going up? Is it trending towards 0? Is it trending toward a line? We need to figure that out. To the negative infinity, is it going up? Is it going down? Is it trending towards a line? Is it trending towards 0? This is what we're trying to figure out. Okay? So we will look at plugging in infinity for x to find end behavior. We are looking at getting an answer of infinity if we're looking at vertical asymptotes. So we are talking about limits with infinities being involved, either equaling a positive or negative infinity, or we are plugging in infinity. All right, let's start with horizontal asymptotes or end behavior. Now, you will do the following. You will, if you're asked this question, look at plugging in positive infinity and negative infinity. For most of our examples, we will tell you which specific direction to look at. Hey, look to the right. What's going on with this function all the way to the right? What's going on with this function all the way to the left? Okay? You will be told which side to look at. But if you are not told and you're just asked to find the horizontal asymptotes, you need to look in both directions. Okay? Okay. And we won't even do this. We're going to get to it later. Okay? And what's key for plugging in infinity is we don't want to plug in infinity, okay? Because if I plugged in infinity just by looking at it, I would say, okay, infinity cubed, okay, that's a big number. Infinity squared, okay, that's another big number. And then I got infinity, and I'm subtracting 3. What this is, I have no idea, okay? And if you ever get infinity over infinity, but you don't understand the type of infinity, the type of number, the growth of our terms, then you're not going to know what's going on. You guys have actually done problems like this before, okay? You've been introduced to the bobs. I hate the bobs. Bob, yo. Bob, no. No. Eats something. I don't want to hear those bobs, okay? Now, if you use the bobs to get your correct answers, that's great. But don't mention a bob in this class, okay? If you're comparing answers with neighbors, talk about what I like to talk about. And what I like to talk about is relative growths of terms. What I will tell you is, hey, 2x cubed compared to 1000x squared, this is going to be growing faster than the 1000x squared, so much faster that I can almost ignore, actually I can't almost, I will be able to just ignore the 1000x squared. Then I'm going to tell you the 10x squared is going to grow so fast that its number is going to be so much bigger than 5x or 3 that we will just be able to ignore the 5x and the 3. And then I will tell you, comparing the x cubed and the x squared, we will have faster growth in the numerator. And that will pretty much dictate what's going on when I look all the way to the right for this function. Don't believe me? Let me show you some things. Let's just take 2x cubed and 1000x squared. Now the idea is to plug in big numbers, right? When I'm talking about plugging in infinity, let's plug in large numbers. And we're adding. And it's like, well, why are you crossing off 1000x squared? Isn't like 1000 times x squared? Isn't that going to be like something cubed? No. The x is being squared. The 1000 is just a multiple. And let me prove it to you. Let's plug in a big number in for x. Okay? A million. To you guys, a million is a big number. Okay? I'm going to plug in a million. If I plug in a million and cube it, I get 2 billion billion, or 2 followed by 18 zeros. Okay, that's a big number. All right, let's do the same thing with plugging a million into 1000x squared. So plugging a million into 1000x squared, I get 1 quadrillion. Another big number, 16 digits long. Now you might be thinking, well, Mr. Messner, if you add this number to this number, won't it change it? Why are you crossing it off? It seems like this is a significant number, that's 16 digits, that you will add to a 19-digit number. It'll get a bigger number, like a much bigger number. But watch what I can do when I divide the two. Okay, now dividing 2 shows relative growths of things. Like 8 divided by 2 is 4. That means 8 is 4 times bigger than 2, right? If I add, something a fourth of the size to something else, it'll change it. Like 1 plus 1/4 is 1.25. 8 plus 2 is 10. Definitely different. But if I divide these two numbers, the first number, which is 1 million being cubed, is 2,000 times the size of the second number, which is a million being squared. 2,000 times the size is essentially like adding 1 and 1 over 2,000 together. Now, if you add 1 and 1 over 2,000, are you going to essentially get a new number, a different number than 1? Like if I add a quarter to 1, I get 1.25. That's different. Well, I get 1.0005. Essentially 1. Just like how we talked about left hand and right hand limits, we're essentially at 1. Now, that's just showing you that the x being squared is not going to make a big difference when you're adding to the x being cubed. This is me showing you that the x squared can be crossed off. If you want further proof, plug in bigger numbers. You know what a bigger number is? A Google. What? Google? The website? A Google, and the name Google came from the number. A Google is the large number 10 to the 100th. It is written by 1 followed by 100 zeros. Now we're starting to talk about large numbers in math terms. Okay, not in terms of like money terms. You would never see a Google of money. You'd see $1 million, but you'd never see a Google. But it is a large number we can use. Watch what happens if I plug in a Google. Well, a Google cubed times 2 gives me something that's 301 digits big. A Google squared is a big number, for sure. It's 204 digits large. But if I divide the two to compare the relative sizes, turns out the Google cubed is 98 digits this times the size of the Google being squared. It's that many times bigger. It's 2 followed by 97 zeros, which is essentially like if you took 1 and added 1 over 2 followed by 97 zeros, which gets you this number. 1 point this many zeros, then 5. And this is me showing you that relative growth is the most important thing. That yes, this is infinity plus infinity, but really it's a very, very large number plus a very, very, very small decimal. That's what you're going to consider, which is why you can cross that off. Which is why if you look in the denominator, you can cross that off and that off. It's insignificant. Okay? And you know that the 2x cubed is going to be growing faster than the 10x squared, which is growing slower. In the guy over here? Well, I'm not sure. 2 to the x or x to the 10th, which grows faster? This one's a little bit easier to show which one's faster. Take a guess with your neighbors. Pick a side. Which one's going to produce bigger values when I plug in 1,000,000? Is 2 to the millionth going to be bigger than 1,000,000 to the 10th power? And let's even go 1,000,000 to the 80th power. What's going to be larger? 2 to the millionth or 1,000,000 to the 80th? Discuss. Pick a side. All right, raise your hand if you think 1,000,000 to the 80th power. Raise your hand if you think 2 to the millionth. All right, good. Here's 2 to the millionth. It is 301,000 digits long. It's got so many digits that it has no chance of showing it on this screen. Okay? 301,000 digits long. Whereas 1,000,000 to the 80th power, big number, sure, but it's only 481 digits long. We're talking about something that's 301,000 digits long versus one that's 481. So if we keep that in mind, first thing we will be able to do is say that's insignificant, the 4,000 is insignificant, and turns out that 2 to the x is going to dictate what's going on in terms of my function, my fraction. Okay? Now, relative growth, that's what we're going to talk about. Faster over slower. We're going to have situations where we're going to have slower growth over faster growth. We're going to have situations where the growth is going to be the same and they'll just essentially cancel each other out. We'll get there. Okay. But before we start doing these problems, we need to understand about the relative growth of things. We need to understand that 3 to the x will grow faster than x to any number, including x to the 30,000. We need to understand that 3 to the x and 4 to the x don't grow the same. If I take 4 and multiply it by itself, it will grow faster than if I take 3 and multiply it by itself. So this is a faster growing function. And then we need to recall the exponential function, e to the x, or really a number to the x, and then the logarithmic function. Remember, every single number to an x power, including e, and we'll stick with e's just because that's the log function we typically use, grows exponentially quickly, okay? A number to the x power has exponential quick growth. This is the log function. I call it the log function. I will use log even though it's read the natural log. It is the inverse function of y equals e to the x. If y equals e to the x grows exponentially quickly, the natural log function grows exponentially slowly. We have to plug exponentially larger and larger values to get just tiny little bits of growth. So, exponentially slow growth. But it grows. Okay. This creates kind of, and go down to this growth of functions, an order, a list of functions who grow from slowest to fastest, or from no growth to the fastest growth. So we will start, and this is when I'm talking about x approaching to infinity, with no growth. A number, plus 1,000, minus 3, plus 2. No growth, so it's just going to be like adding nothing when I'm plugging in large numbers. Then, exponentially slow growth, the log function. But it grows. 2, x to a power. where different powers of x will grow faster than other powers of x. X to the fourth will grow faster than x cubed. That makes sense? But those will not grow as fast as a number to the x power. Knowing that 4 to the x grows faster than 3 to the x. In AB calculus, we stop there. If we wanted to keep going, and if we were in BC calculus, we would talk about factorials actually being faster than number to an x power. And then we'd actually finish off with x to the x. You won't see these in this class, but cool to look at it. And you can start plugging in big numbers into a factorial, into a number to the x power. You'll see that, okay? So we're going to keep this in mind, slow growth, fast growth. But it actually gets a little complicated with these number to powers. So let's just underline this and highlight this and write, be careful. Be careful. Why do you need to be careful? Because if I'm looking to the right with an exponential function, yeah, it's going up, it's going to get larger and larger and larger. We will say this will be approaching infinity. Three to the infinity, infinity. But if I go in the other direction, if I look to the left, if you look to the left of e to the x, you'll see this. Or if you plugged in negative infinity, you will find that this answer is not negative infinity. What is it? Discuss with your neighbors. It does exist. Now, this leads us into understanding what 1 over a very large number is. Remember a rule of exponents, negative exponents, is the same as 1 over the number to the positive exponent? Okay, well, we should start thinking about a number, any number, divided by infinity. Well, take 1. Well, infinity is not like a number, it's more like a concept. It's like if I continue to grow like this, what is happening to these fractions? They're getting smaller and smaller and smaller, getting closer and closer and closer to 0. We actually say that that's 0, which is why if I'm going in the opposite direction, numbers don't grow, neither do number to the x's. That's important. You don't have to worry about the log function because it doesn't exist. You can't plug in negative values. So you just have to go x to the number would be the fastest in that direction. There's a different type of function we'll talk about in a second, but here we go. Now we're ready to tackle things. Here is how I'd like you to evaluate limits at infinity. There's 3 situations. The first is that the growth is faster in the numerator. So knowing that this is insignificant, this is insignificant, this is insignificant, I see that I have faster growth because it's x cubed compared to the x squared, which is slower. I think about this set of fractions that I'm just going to show you, where the numerator will grow by a multiple of 10. Whereas the denominator will just be added to 1. This is faster growth. This is slower growth. What is happening to these numbers as I look at one fraction to the next fraction to the next fraction? What is happening? Discuss with your neighbors. Compare 10 over 1 to 100 over 2 to 1,000 over 3 to 10,000 over 4. What is happening as we go from one fraction to the next fraction? $10, $50, 333.3333, 2,500, I think. Yeah, that's right. 2,500. The numbers are getting larger and larger and larger. When you see faster growth over slower growth, your fractions will get larger and larger and larger. You'll be approaching larger and larger values. That's why it's Bob Yo. I don't know what that means. Okay? Now, there's another way you could do it. And this might help us in the future. Right now, it's okay. Is you could just say, all right, well, if this is insignificant, this, and this, why don't I just write 2x cubed over 10x squared? Doesn't that simplify to just be 2x over 10? And can I just plug in infinity and like 2 times infinity is infinity divided by 10 is infinity? Yes. That's another way to get that answer. It's not really conceptual. It kind of is conceptual. It's a little bit more algebraic. It works in some situations. It actually doesn't work in all situations. Like this situation. I'm plugging in very, very large positive numbers. Okay, I think about relative growth of things. X to the 10th, insignificant compared to 2 to the x. 4,000, insignificant compared to 80, x to the 80. And then comparing these two, 2 to the x goes faster than x to the 80. So you think about a situation where I have faster growth in the numerator versus slower growth in the denominator. Think about this set of fractions where you have numbers in the numerator growing faster than numbers in the denominator. What is happening as you go from one to the next to the next to the next? The fractions are getting larger and larger and larger. Now, you cannot do that same algebraic technique with this example. I can't like cancel things and then have infinity. I just need to know that this is faster over slower. But we need to be careful. I said positive infinity here. I said positive infinity here. It's not always going to be positive infinity if you plug in positive infinity. If I, and go ahead and do this, plugged in a negative right in front of that 2, my answer would change. It would change tremendously. Because, sure, I have faster and slower, but I have like a negative, and this helps when you look at it algebraic, in front of that 2. If I have negative 2 times infinity, that's going to give me a negative infinity. Negative times a positive is a negative, right? So, our coefficients and our directions do matter. Your answer won't always be infinity, 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 infinity. Here, if I just put a negative in front of this 2, all of a sudden, as I look to the right on my function, my end behavior would be going down. Okay? If I put a negative 2 in front of the x to the 80th, it would also be negative. Because it'd be a faster, but it'd be a positive number. But in the denominator, it'd be a slower growth, but it'd be a negative number. Negative. Here, faster but a negative, slower but a positive, negative. You can think of it that way as well. So you need to be careful with your signs. Okay? Now, what did we just discover? We just discovered that for this function, if I look to the right, and this is with the negative in front of it, I'd be trending downwards. For this function, if I look to the right, and let's go back to the original. If I looked to the right, I'd be trending upwards. and behavior. That's what we're looking at, okay? Okay, now, with you guys being careful of your signs, all of a sudden I'm plugging in negative infinity. Okay, look at the relative growths, numerator, denominator, cross out the things that you got going. Think about plugging in a negative value. Figure out, is your numerator going to be positive or negative? If your denominator is going to be positive or negative? And then give me the correct infinity, because I'm telling you this is a situation where it's going to be faster divided by slower. Go. Check with your neighbors. Since the negative 20x and the x are insignificant, you do not have to worry about taking those into account when you're figuring out the signs of things. Discuss with your neighbors. Is the numerator positive or negative? Is the denominator going to be positive or negative? Go. Taking a negative and I'm squaring it. A negative squared positive. You ready? Two ways you can think about it. The answer is positive infinity. A negative value cubed retains its sign. Negative times a negative times a negative is a negative. So a negative value cubed retains its sign, but times negative 4, the numerator is positive. A negative value squared, positive, times 1,000, stays positive. That is one way to figure out we are going to be trending up if we go to the left. The other way would be to algebraically simplify these things. You can write that we have essentially the limit as x approaches negative infinity of negative 4x cubed over 1,000x squared, which simplifies to be negative 4x over 1,000, negative 4 times negative infinity, positive infinity. I would say this will be easier and will work for all situations. Okay. Be careful here. Don't cross off the 20x. Why? Discuss with your neighbors. Why? I'm not going to cross off the 20x. Nope, but close. Anybody have a confident answer of why I'm not going to cross off the 20x, but I would cross off the 4 to the x? Mr. King. This, in this direction, just like I told you, when we are going for x approaching negative infinity, this is a no-growth function. This is going to 0. This won't grow. So that's gone. In the numerator, with the cubes and the squares, the cube will grow faster than the square. All right, now, be careful with your signs. Tell me, positive infinity, negative infinity. Go. It is faster over slower because we have an x cubed and a 20x. But positive over negative. Or negative over positive, or positive over positive. Figure it out. Take this negative and cube it. Everybody, tell me, is the numerator positive or negative? With a little bit of confidence. Okay. Take negative large numbers, plug it in to this 20 times x, but then subtract it. Is the denominator negative or positive? Oh, so little confidence. 20 times, thank you. Positive is correct. I appreciate. Do we see why? 20, like you can either distribute this negative plus or minus. You can either do that, negative 20 times negative infinity, and negative times a negative is a positive, or just say 20 times negative infinity is negative, subtracting a negative becomes a positive. This turns into positive infinity. Sorry, negative infinity. So we are careful. Great. Next situation. Slower over faster. Now, you can think about a number divided by infinity. We already talked about it. 1 divided by, continue to add zeros. Continue to add zeros, add zeros, add zeros, add zeros. What's happening to this fraction? Getting smaller and smaller and smaller, approaching 0. Or thinking about things in terms of relative growth. Say you're growing in the numerator, but you're not growing as fast in the numerator as you are in the denominator. What is happening if we look from one fraction to the next one to the next one? 0.1, 0.02, 0.003, 0.0004. These fractions keep getting smaller and smaller and smaller. They are approaching 0. So whether it's a number over 0 or a number over infinity, or slower growth divided by faster growth, your fractions get smaller and smaller and smaller. They approach 0. So we literally, and thankfully, 0, we don't have to worry about the sign of 0 just yet. Okay, we will actually in a little bit. But thankfully, if I just see x to the 4th, okay, whatever, that doesn't matter. That's slower than x to the 5th. Boom, 0. Do I care that it's negative and positive? No. Okay, being careful. I'm plugging in positive infinity. The log function is the slowest growing function. Get out of here. The 500, no growth. Get out of here. 2x compared to e to the x. Slower over faster. I don't care if it's positive or negative. It will be approaching 0. That is my end behavior there. Now, approaching negative infinity. Thankfully, for these end behaviors, the sign actually doesn't matter. Don't care, don't care. X to the 5th compared to x to the 5th. X to the 6th, slower over faster. Approaching 0. I could also, if I wanted to, and this is kind of the algebraic way to do things, and it only works when you have x to a power over x to a power. It'll work in the future. Is I could actually simplify this. This becomes 5 over x, and this becomes like 5 over infinity. It's another way to see that the answer is 0. Oh, great example right here. This negative infinity actually does matter. Because if it was positive infinity, you'd say, oh, faster 10 to the x, slower x cubed. But I'm approaching negative infinity. So tell your neighbors why that matters with this problem and why it's not faster over slower. So yeah, I missed one. What do you think? Why? Yep. Yep. This is a no growth situation when I'm plugging in negative infinity. So this doesn't matter. 2x doesn't matter compared to the x cubed. You have x squared over x cubed. You got slower over faster. If you wanted to do it algebraically, you could. You'd have negative x squared over x cubed. Find the limit as x approaches infinity, or negative infinity. Negative 1 over x. Negative 1 over infinity. Still approaching 0. Fortunately, we don't have to worry about if it's 0 like from the positive side or 0 from the negative side, but we will when we do a horizontal. Okay. I'm going to do this first example algebraically. 2x, 5, 1, get it out of here. It's like adding very, very small numbers to very, very large numbers. I got, and this is helpful if you see it algebraically. Just negative 4x cubed will determine what's going on with my function. X cubed will determine what's going on with my function. Watch what happens. Growth divided by the same growth. You can see how it will cancel and just leave a coefficient. We're finishing up the lesson. Do you have a question, or are you? When we're done with the lesson. Cool. Okay. So essentially, what we have going on is like some number times the same growth over some other number times the same growth, and the same growth will cancel. And you're just left with these coefficients. Okay. I see e to the x. I'm going to be careful. I realize I'm plugging in positive infinity. So e to the x would be considered one of the fastest growing functions. 200x doesn't matter. Log x, slowest growing function. X squared, not going to go quickly. I just have 3e to the x over 5e to the x. We can see those cancel, leaves me with 3/5. Okay. I'll do this one. This is easy. You'll do the next one. Next one's tricky. Does it matter that it's negative? No. The growth will cancel. The negative divided by a negative. Excuse me, will cancel. So I don't care that I'm plugging in negative infinity because they'll end up canceling each other out no matter what, as long as the growth is the same. Try this one. Be careful. Good. 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 Very, very, very good. Because I'm plugging in this large negative number. This is a no growth. That's a no growth. It's just the negative 3x squared over the 5x squared. The x squareds will cancel, leaves me with negative 3/5. Okay? Good. Now, for these next groups of situations, I don't tell you which direction to look at, okay? So I'm just saying, analyze the end behavior, find the asymptotes, okay? You need to make sure you're looking in both the positive direction, so to the right, and all the way to the left. So make sure you think about both. going to switch this one up for you guys. I'm going to do 1 minus 2x cubed. Okay? Faster over slower, but faster negative, slow positive, negative infinity. Still faster over slower. So it'd be a faster positive. It'd be a slow positive. Positive infinity. Same over same. 2/3, 2/3. Slow over fast. 0, 0. Those are the easy ones. The first one, the tricky one, actually, this first one, the fast over slow. Be careful with fast over slow because of signs. Be careful with fast over slow because of signs. Okay? Now, these are great. See these frequently on AP tests. They ask, find the horizontal asymptotes to this function or this function. And the first thing students don't do is they don't look in both directions. They only look to the right, but they don't look to the left. Please look in both directions and tell me the 2 different answers that we will get depending on the direction we go in. Because you get 2 different answers. Go. Check out my answers to the guy on the left. And if you got these, great. If you didn't, see what happened. And then do the one on the right. The one on the right's tricky as well. I'll tell you right now that 5, 6 is not the answer for that positive infinity. We're continuing on with the notes. Okay. Who can tell me why 5, 6 is not the answer? Who can tell me what is the answer for K as we look all the way to the right? It is 0, Ms. Biggs. Why? Yes, it is faster. We have a situation where we have slow over fast. Slower growth over faster growth. The x squared and the x are gone, but different growth. Just like how x squared does not grow as fast as x cubed. 2 to the x does not grow as fast as 3 to the x. So I know you see numbers and people like think, oh, I got to be using those numbers. It's the same growth, but it's not. X squared, x cubed, different growth. 5 to the x, 6 to the x, different growth. So what is the answer, Ms. Biggs? What did you say? Good. Slow over fast, 1, 2, 3, 4, divided by 10, 100, 1,000, 10,000, smaller, smaller, smaller. Okay, negative infinity. They'll stop over there. Now, I have fast over slow. But what are my signs? This one would be a good one to do algebraically to confirm signs, like negative x squared over negative x. Like, oh man, those x's, those negatives cancel, the x's cancel. It's just x. Plug in negative infinity. I should get negative infinity. Okay? If you kind of plugged in negative infinity right here and here, you have negative infinity squared, which is a positive, but then it would be a negative because of the minus sign. You'd have negative infinity, but you'd have minus negative infinity would turn into plus a positive. That is how you can get negative infinity. It might be easier if you simplify it. Okay, great. Please be careful crossing things out. A lot of students see this 5 and they're like, oh, insignificant, it's gone. It's actually very significant. Because what happens if I look at this as x approaches infinity? What do I get? This one. Very small number approaching which value? 0. Okay, so as x approaches infinity, this is approaching 0. Well, if I cross this off, my answer would be 0. But no, I have 5 minus 0. That's 5. If I went in the negative direction, it'd be the same. Don't cross off the 8 or the 8 minus, you know, like the minus sign is big. If x is approaching positive infinity, this would approach negative infinity because it's 8 minus infinity, negative. If we went the opposite direction, we'd be approaching positive because of the signs. Okay? That, my friends, is horizontal asymptotes. That's your bobs. That is relative growths and fractions where growth is bigger, either in a numerator or denominator. What happens to your fractions? That's what you should be thinking of. You should be thinking of this situation getting smaller, 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 or the situation flips where the fractions would get bigger, bigger, bigger. Question? It would be 5 for positive and negative infinity. If x is approaching negative infinity, would that is equal to? No, it would still be 0, so it would be 5 for both right and left. Oh, we got more actually. Sorry. These are tricky ones. Oh, we got these two. Man, sorry. Asymptotes. Would I say I have faster over slower, slower over faster, or same over same? Discuss. If you said same over same, you're right. Because we have a square root of an x squared. A way to see that. Get rid of that 5x, get rid of that 3. We know they're insignificant. 2x over root 9x squared. Property of an exponent. If I have root 9x squared, I can write it as root 9 root x squared. Well, that simplifies to 3x. Same. Now, be careful. 2/3 is the answer. If I went in the other direction, negative infinity, you might be thinking, oh, 2x root 9x squared, 2x root 9 root x squared, 2x, 3x, 2/3 as well. This one is wrong. Everything's right, but we got to think a little bit harder. Can anybody tell me what the correct answer would be? Still same over same, so it does end up having 2/3. Here's the difference between the two, which will lead to different answers. What's 2 times a negative value? A negative. What's a negative value squared? Negative 2/3 is the answer. So with these limits at infinity, with these square roots, we actually have two asymptotes, one in a positive direction, one in a negative direction. It's really cool how it ends up working out like that. All we need to do is just be careful about our signs, just like how we thought about, oh, negative over positive, negative infinity. You know, now it's going to just be something else. So try this one out for me. Now, you might think that the answer is -3. So be careful with these things. And it kind of goes back to what is the square root of an x squared. When I was solving equations, when you solve equations, x squared equals 9. You take the square root of both sides. The answer is not x equals 3. Plus or minus 3. Now, what some people think is that, oh, that's because the square root of 9 is plus or minus 3. But that's actually not true. The square root of 9 is just 3. The function root x is just this. It's not 3 and -3. But what we do say could have been positive or negative was this x. We say the square root of x squared is either the positive or the negative x, which is how, and it's actually we say it's the absolute value, but that's how we then transfer that plus or minus over to the 3. So don't tell me that the square root of 9 is plus or minus 3. The square root of 9 is 3. It's just the square root of x squared that is the plus or minus. So that is why you will be careful. And you will realize, oh, I'm plugging in negative infinity. This is ending up as a positive when I plug in negative infinity. This will be a positive as well. Positive, positive, positive 3. -6 times negative infinity, positive. Negative infinity squared, positive times 4, positive, rooted, positive. Got it? Careful with signs again. Really, I should have like a plus or minus down here, and then you should go back and like decide later. Questions? All right. Well, let's talk about sine and cosine real quick before we move on. My friends, sine and cosine look like this. Now, the largest y value it could have is 1. The smallest y value it could have is -1. No matter what value I plug into sine, whether it's sine of 10, sine, and you can use pi or whatever, sine of 1,000, 10,000, sine of 10 to the 100th, you know that it's between or equal to -1 and 1. -1 and 1. -1 and 1. So we say that this limit, first of all, does not exist, but more importantly, we say this is a no growth function. You can think of it almost like a constant. So if you see sine x over x and you're plugging in infinity, you can almost think of this as being a number. Really, you know it's between -1 and 1. And you take something between -1 and 1 and divide it by infinity, that's going to be approaching 0. Which means if you have x over 2x plus sine x, if you wanted to cross something out, the 2x or the sine x, you're going to cross off the sine x because it doesn't grow, whereas the 2x does grow. Log of x will grow faster than sine x. Sine x doesn't grow. This ends up being over same. X over 2x simplifies to be 1/2. It's one of those, use the coefficients. Okay? So if you go back in your notes to our list of growths, guess what? No matter which direction you go, sine x, cos x are no growth functions, both as x is approaching infinity and as x approaches -infinity. Okay? Okay, so let's look at these two. This is a little bit different. Sine x isn't in it, like x is here. I challenge you to figure this out by yourself and tell me what the answer is. If you get the answer, shout it out, and I'll tell you if you're right or wrong. And I will say, good job if you got it right. And I will say, don't worry if you got it wrong, because it's tricky. Think about plugging in a large value for x. What happened? Anybody? One. Why, Miss Courier? Very good. Second one is 0. Very good, because it'd be like the sign of 0. 0. Okay, cool. All right, that was horizontal asymptotes. We handled every single type of example you're going to see in this class. Switching gears, vertical asymptotes. It's very important to understand that we know from last class that at x equals 3, we will have a vertical asymptote. That's a non-removable discontinuity. We know that, and I told you last class, because you get a number divided by 0. But why is that telling me I have a vertical asymptote? That's what we will get into a little bit more today. Our goal today, knowing that at 3 we have a vertical asymptote, is to figure out, by analyzing each side of 3, what is my function doing or behaving to the left and to the right? The question is my function going up to the left towards positive infinity? Is it going down to the left towards negative infinity? To the right, same thing. Is it going down? Is it going up? Okay. Now, we have infinities as y coordinates. For horizontal asymptotes, we were looking at infinities as x coordinates, which is why we were plugging in, very, very large values. Switching gears, and we are plugging in numbers to one side or the other, an x coordinate, and now we are talking about our y's being either plus or minus infinity, and we'll have to figure that out. Do we understand the difference here? Horizontal asymptotes, plug in infinity for x. Vertical asymptotes, we're going to get infinities as y's. All right, here's the key. Why do we have a vertical asymptote at a number divided by 0? It's because of this fact. If I divide anything by something infinitely small, what happens if I keep adding zeros to this fraction? It's going to get bigger and bigger and bigger. If I continue to add more and more zeros here, and I have taken something that's a number and divided by something that is approaching 0, I will get something very large. That is why you see a number over 0, that is an indication that we're talking about our infinities. That is an indication of it being a vertical asymptote. That is why I told you, if you see a number over 0, it's going to be a vertical asymptote, not a whole. Okay? Now, what is important, say this was a positive number. If this was an infinitely small number and positive, this would be an infinitely large number and positive. But if this was an infinitely small negative number, positive divided by a negative, that would change into an infinitely large negative number. So we now need to be careful about if we're talking about very small positive or very small negative. I'm going to use 0 from the right and 0 from the left to denote a very, very, very small positive or a very, very small negative. Assume there's like an infinite amount of zeros. Okay? So that's the notation I'm going to use. And I'm going to keep in mind that if I take a positive divided by something infinitely small but negative, I would be infinitely large and negative. Positive divided by something small and positive, positive. So all these sign rules just still hold. Okay? And this is how we're going to tell if around an asymptote we are going up or down, because we're going to get an answer that looks like this, and we're going to be able to say, oh, I'm going up, or oh, I'm going up from this side. Okay? So here we go. I'm looking at f of x equals -1 over x plus 1. I know when the denominator equals 0, I have a vertical asymptote. So I have a vertical asymptote at x equals -1. Now I need to discover the behavior around this asymptote. Well, let's look at first to the left of -1. This is what I'm going to do. I'm going to pop over here to this number line. Number lines are going to help us, because I know to the left of -1 is something like -1.0001. To the right of -1, something like -0.999. I'm going to think about taking -1.0 plugging in for x. And then I'm going to think about, and you don't have to write this down, you can just think about it, what happens when I add those two numbers in the denominator together. I'm going to get something close to 0. But it's your job to figure out if it's close to 0 and positive or close to 0 and negative. Go, figure it out. Discuss with your neighbor. Is this plus this close to 0 and positive or negative? It's negative, because negative 1.0001 is a little bit larger than 1. So we have more of the negative, which is why what I'm going to write is something very close to 0, yes, but close to 0 and negative. Okay? Now, what is a negative number divided by something infinitely small and negative? Positive infinity, something infinitely large and positive. This is telling me if I look at -1 to the left, I'm trending upwards. Now, -1 from the right, I'm thinking about plugging in -0.99999. You think about this, you don't have to do it. Adding these two numbers together, you should realize the positive value is bigger than the negative value. We're approaching 0, but we're positive. That gives us negative infinity. There's my behavior around my asymptote. Now, if I asked you, what is the limit as x approaches -1 in general? Notice I don't have a left or a right. What would you say? D&E does not exist. Correct. Let's look at another example. We got 4 from the left and 4 from the right. Number lines sometimes help me. 4 from the left, 3.999. 4 from the right, 4.0001. If I plug in 3.999 and subtract 4 from it, I'm going to get something that's close to 0 but negative. But guess what? I square that. A negative times a negative becomes a positive. This is why we should get negative infinity for this one. So 4 is my vertical asymptote. To the left of 4, I'm going down towards negative infinity. 4 from the right, -5 over 4.001 minus 4. That's like 0 from the right squared. That's still a very, very small positive number. That is also negative infinity. So this is going down there. Now, if I ask you what is the limit as x approaches 4 of this function, you would say does not exist, and you would be correct. Or you could say negative infinity. To the right, we're both trending towards negative infinity. So the left-hand limit equals the right-hand limit. They don't really equal each other. We never like to talk about equality with infinities. However, on the AP exam, you need to be prepared to have both answers. But this is only because they are both going in the same direction around our asymptote. Okay? Okay. Couple more. Just talked about 4 from the left, so I know 4 from the left is 3.999. Okay? Now, you're going to think about plugging that in. But I'm going to tell you, you won't have to worry about it in the numerator. That you could just plug in 4 into the numerator, and you can say 4 minus 5 is -1. But in the denominator, you do need to plug it in, and you need to figure out the sign of this infinitely small number. 3.999 minus 4 is going to be something infinitely small and negative. Why do I not care about this being positive or from the right or from the left? Any ideas? Because it's not close to 0 is correct, but why does that matter? Because to the left or to the right of -1, not that big of a difference. But to the left and to the right of 0, huge difference. What's the huge difference to the right and to the left of 0? The sign. The sign makes a huge difference when we're doing calculations. But here, no matter if you're to the right or to the left of 1, you're still negative. But this, huge difference. Now I got a negative value divided by something infinitely small and negative, infinitely large, positive. Okay, you guys try the next one, please, for me. I gave you the number line because you need to be careful. Yeah. So you did the tangent. Sine is just the vertical, which is just this, but it's negative because you're going down.
Thank you.
Sine's just opposite. I gave you the number line because a lot of people on the negative side don't think about right and left the same. -3 from the right is like -2.999. Adding 3 to that, I'm getting something infinitely small and positive. But in the numerator, -3 plus 1, -2, I don't care that it's -2 from the right or -2 from the left. Negative divided by something infinitely small and positive, infinitely large and negative. Okay, 2 more. The vertical asymptotes are quicker than the horizontal asymptotes. I'll do this one, you guys do this one. Ready? First, there's that. Square it. I'm going to get a number that's just a little bit bigger than 4. Is it exactly 4.00001? No, I don't know, but I do know it's going to be bigger than 4 because -2 times -2 is 4, but if I add a little bit more and multiply by itself, it's going to be a little bit bigger than 4. That is telling me that I have a positive number divided by something infinitely small and positive. This will be approaching positive infinity around this asymptote at -2. Last one, do the one on the right. Check your answer with the neighbor. Number less than 3 is 2.999. If you square 2.999, are you going to get a number a little bit bigger than 9 or a little bit smaller than 9? Smaller. So, think about that. -2 times 3, -6. 9 minus something just a little bit smaller than 9, very, very close to 0, but it's positive. That's why the answer is negative infinity. So I am trending down to the left of 3 where we have a vertical asymptote.